morning. So today we are going to start our discussion on use of neural network for pattern recognition. So far what we have discussed, initially we started discussing about the Bayes decision theory, where we have seen that the classifiers are to be designed using the probability density function of the training samples, and later on we have gone to non-parametric classification techniques, where we have seen the different types of criteria functions like perceptron criteria, relaxation criteria, or minimum squared error criteria, which are to be designed, which are to be minimized for designing of a linear classifier. So before I actually go to this use of neural network for pattern recognition, let me briefly tell about two more techniques of non-parametric pattern classification. So one of the non-parametric technique for pattern classification is called a nearest neighbor rule. Or nearest neighbor classification. Or it is also called NN rule. So when you use this nearest neighbor classification technique, what you do is instead of trying to design any classifier or any discriminant function for any of the classes, what I have is I have a set of training samples, the training samples coming from different classes. So if it is a 2-class problem, I will have training samples coming from 2 different classes. For a C-class problem, I will have training samples coming from C different classes. In nearest neighbor classification, what we do is whenever an unknown sample is given, we have to classify this unknown sample to one of the classes for which I have the training samples. So what I simply do is I simply find out the nearest training sample which is nearest to the unknown sample. That means you try to compute the distances from that unknown sample to all other training samples which are provided, okay, and you find out the minimum of those distances. So whichever sample is nearest to the unknown sample or the distance is minimum, I know what is the class belongingness of that particular sample, of that training sample which is nearest to the unknown sample. So accordingly, you classify this unknown sample to the class of the training sample which is nearest. Okay. So I have situation like this. So if I have a set of training samples, so these are the training samples which belong to one class, and suppose these are the training samples that belong to another class, okay, and suppose I have an unknown sample which is somewhere over here, okay. So if these samples actually belong to class omega 1 and these are the samples which belong to class omega 2, okay, I just find out that which sample is nearest to this unknown sample. So find that the distance between this sample and this sample is minimum. So the nearest sample is this one, and this sample belongs to class omega 1. So I simply classify this unknown sample to class omega 1, okay. But this particular approach has a problem. The problem in the sense that a sample nearest does not mean that it is most probable class, okay. So I can have a situation something like this. So I take 2-dimensional feature vectors having the feature components x1 and x2, okay, and the samples are for one class something like this, and for another class the samples may be something like this. Okay. So, I say that these are the samples, training samples taken from class omega 1, and these are the training samples taken from class omega 2. Okay. And in over here, if the unknown sample is somewhere at this position. Okay. So, you find that as before, this unknown sample will have a minimum distance from this training sample which belong to class omega 2. Okay. So, I will classify this sample to belong to class omega 2. Okay. However, you find that here I have a single point, a single sample from class omega 2. Okay. Whereas, I have more number of samples from class omega 1, okay, which may actually or which should actually influence the classification of this unknown sample. Okay. But without looking at the density of the training samples, we are blindly classifying this unknown sample to a class which is nearest to one of the training samples. Okay. So, this sort of nearest neighbor rule does not take into consideration the maximum probability of a class. Okay. So, a solution to this is that instead of taking a single point which is nearest to the unknown sample, you take a pre-specified number of points which is more than 1. Okay. Then try to classify this unknown sample to one of the classes based on a voting mechanism which is given by those training samples where the number of training samples is pre-specified. Okay. So, accordingly, we have a rule which is k nearest neighbor rule. Or KNN classification. So, over here what you do is, instead of taking a single point which is nearest to the unknown sample, you take k number of points, k number of training samples which is nearest to the unknown sample. Okay. And these samples, this k number of samples may come from a single class, may come from multiple number of classes. And out of these k nearest neighbors or k nearest training samples that we get, you try to find out that which class is mostly occurring, is maximally occurring in that k number of samples or k number of training samples. So, whichever class is maximally represented in that k number of samples, you classify these unknown samples to that particular class. Okay. So, considering that,
so how will that this k number of samples from omega 1 class or omega 2 class?
It may be from any class. I just want that I have to have k number of samples which are nearest to the unknown sample. I do not bother about whether it belongs to class omega 1 or it belongs to class omega 2. Okay. And once I have that k number of training samples from whichever class it is, without any class consideration, you take k number of training samples which are nearest to the unknown sample. And within that k number of nearest samples, now you find out that from which of the class I have got maximum number of samples, right. So, which class is maximally represented in that k number of samples. So, whichever class is maximally represented in that k number of samples, I classify the unknown sample to that particular class. Okay. So, coming to this same example, so this is the position of the unknown sample, okay, and these are the samples which are from class omega 1, these are the samples from class omega 2, right. So, what I do is, I try to incorporate k number of samples which are nearest to this. Okay. So, for doing that, what I have to do is I have to find out the distance of the training samples, whether it is coming from class omega 1 or it is coming from class omega 2. Irrespective of that, I have to find out k number of samples which are nearest to this unknown sample. Okay. So, suppose I decide the value of k is equal to 5. Let us take any value. Okay. So, I will take 5 samples which are nearest to this unknown sample. Obviously, this is nearest to this training sample. So, this will be included in that 5 samples. Among the remaining, suppose these 3 are the samples, or maybe this one. So, these 4 of the other samples which are also nearest to this unknown sample. So, I have selected 5 number of samples. Okay. Out of 5, you find that there are 4 samples which are coming from class omega 1, and I have only 1 sample which is coming from class omega 2. So, it is class omega 1 which is maximally represented in those 5 training samples. Okay. So, I have to classify this unknown sample x to class omega 1 rather than class omega 2. So, you find the difference that if I go for simple nearest neighbor rule, that is, I find out one training sample which is nearest to the unknown sample. In that case, this unknown sample is classified to class omega 2, whereas if I take 5 nearest samples and out of those 5 I find out which class is maximally represented, and here it is class omega 1 which has 4 samples out of the 5, whereas class omega 2 has got only 1 sample out of 5. Okay. So, accordingly, this unknown sample is classified to omega 1 rather than class omega 2. Okay. Now, naturally, if I go for the nearest neighbor classification where value of k is equal to 1, okay, the error rate or the error bound will obviously more than the error bound that you get by using Bayes decision or Bayes minimum error classifier, because in case of Bayes minimum error classifier, we classify an unknown sample to a class for which the probability of a particular class is maximum. Okay. And in case of a single one NN or nearest neighbor classification rule, I am just taking a sample which is nearest to the unknown sample, and that particular sample, training sample, may be just an offshoot. Okay. I may not have other training samples nearer to this belonging to the same class. So, accordingly, the probability of that particular class in that region is very less. Okay. So, naturally, the error that you get in case of nearest neighbor rule is more than the error that you get using Bayes minimum error classifier. Whereas, if I go for this KNN classification, okay, where I am trying to find out that which class is maximally represented in those k number of training samples, okay, and it can be shown that if value of k as well as value of n by k, where n is the total number of samples, okay, is very large, in that case the error bound of KNN classification approaches the error bound of Bayes minimum risk classification. The reason is very simple, that if k is very large and also n by k is very large, then the number of samples within a small region, that gives you a good approximation of the probability density function of the samples belonging to different classes. Okay. So, in the limit when k becomes very large as well as n by k becomes very large, the error bound given by KNN classifier approaches that of the Bayes minimum error classifier. Okay. Now, following this, if I go for simply nearest neighbor rule, I should be able to find out what is the decision boundary between different classes. Okay. So, let us take a very simple example, something like this. Say I have a number of samples. So, this is one sample, this is one sample, okay. This is one and this is one, and I may have another sample somewhere over here. Okay. And let us assume that this sample belongs to class say omega 1, this sample belongs to class say omega 2, this sample belongs to class omega 3, this one belongs to class omega 4, and say this one belongs to class omega 5. Okay. Now, following nearest neighbor rule, if I want to find out what is the decision boundary which separates all these different classes. Okay. So, you find that whenever I go for nearest neighbor rule, the nearest neighbor classifier is nothing but a minimum distance classifier, okay, because the class to which I am classifying this unknown sample, I have one sample from that class whose distance from the unknown sample is minimum. Okay. So, naturally, this is nothing but a minimum distance classifier. And if I have a minimum distance classifier, then the decision boundary between the two classes, where I have representatives of the two classes, okay, then the decision boundary is nothing but a perpendicular bisector or orthogonal bisector of the line joining those two exemplar samples or those two representatives. Okay. So, following that, you find that the decision boundary between class omega 1 and omega 2 will be an orthogonal bisector of the line joining omega 1 line joining these two samples. Okay. So, the decision boundary that I have is simply this, and it will be extended on this side, okay, as regards omega 1 and omega 2, and it will be extended on this side. Now, coming to the decision boundary between class omega 1 and omega 5, okay, that will also be an orthogonal bisector of the line joining omega 1 and omega 5. Okay. So, this decision boundary will be simply this, right. Similarly, the decision boundary between classes omega 1 and omega 3, that will be orthogonal bisector of this line. So, this particular decision boundary, so it will be something like this, will be this one. Okay. In the same manner, the decision boundary between omega 3 and omega 5 will be this, between omega 5 and omega 4 it will be this, between omega 2 and omega 4 the decision boundary will be this, between omega 3 and omega 4 the decision boundary will be this, and between omega 2 and omega 5 the decision boundary will be like this. Is it okay? So, if I follow the nearest neighbor rule, I can very easily find out the decision boundary among different classes for which I have the training samples. Is it okay? So, these are the different non-parametric techniques for classifier design or for classification of unknown samples to one of the known classes. Okay. So, now let us start our discussion on use of neural network for pattern recognition. Okay. So, when we talk about a neural network is nothing but a computational model which tries to imitate the human brain. Okay. So, when we talk about our human brain or human nervous system, this actually consists of a number of numerous nerve cells. Okay. And in the nerve cell, The nerve cell is something like this. If you draw any particular nerve cell, it goes like this. Okay, where this whole thing is a cell body. These are what are called dendrites, or sensors. Okay, inside I have the cell body, okay, and these fibers, these are actually called axons. Okay, so these dendrites or the sensors, they actually sense different stimulus. Okay, and that signal is carried to the brain by these actions. Okay, and depending upon what kind of stimulus or what kind of sensing this cell body has done, the brain takes a particular action, decides an action, and sends that information to or different muscles through a set of such neurons, and then we take certain action by activating the corresponding muscles. Okay, so when we talk about the neural network also tries to imitate a functionality something like this. Okay, so a neuron model for machine intelligence or for artificial intelligence will be something like this. Say I have to have something like a cell body, okay, and then I have to have a set of inputs which act as dendrites, okay, and then I have to have an output which will act as the action, right. So what I have is, I give the feature vector as input to this neuron, okay, and our feature vectors are having different components x1, x2, x3 up to say xn, if I have n dimensional feature vector. Okay, then the cell body performs an weighted summation of these different feature components. Okay, and weighted sum is fed as an input to a nonlinear function, and in most of the cases this nonlinear function is some sort of a threshold function, okay, or it may be a continuous nonlinear function as well. Different types of neural networks use different types of nonlinearity, okay, and this is our output. Let us call it as y, okay, and because this will be, this particular cell body will compute the weighted summation of these different feature components. So I have to have the corresponding weights, okay. So those weights are say W1, W2, W3 and W4, okay. So what I have at the output of this is just like summation of Wi xi, where I varies from 1 to n, okay, and on this I have a nonlinear function f, and that is my output y, okay. If I use this nonlinearity as a simple threshold function, then what I will have is, if this nonlinear output, if it is greater than threshold, okay, I set y to 1, and if this is less than or equal to threshold, I set y to 0. Okay. So, having this kind of functionality, you find that it has a very close similarity with one of the linear discriminators that we have designed earlier. Okay. That is, we have said that if g I x is greater than 0, it belongs to some class. If it is less than 0, it belongs to some other class. And if I have a linear discriminant function, that g I x is nothing but this summation of w I x I varying from 1 to n, where my feature vector is n dimensional. Okay. And if this function is greater than threshold, I set y is equal to 1, indicating that this x belongs to one class. If this is less than or equal to threshold, I set y equal to 0, indicating that this x belongs to the other class. Okay. Earlier we have said that if it is equal to 0, then x actually belongs to the boundary. I can also put that condition over here. If this function weighted sum becomes equal to 0, I will not take any action. Okay. Whereas, if it is less than 0, then only I will set y equal to 0. So, accordingly, this function will be different, or the threshold function will be equal to will be different. Where if this weighted sum becomes equal to 0, then I will not take any action. Okay. However, in case of linear discriminant function, we have seen that before you go for designing the classifier, you have to append 1 to the feature vector. So, you get a modified feature vector, and this purpose of this modified feature vector is that I can incorporate a bias weight which are different corresponding to different classes, that is WI0. Okay. I can also incorporate the same bias within our neural model. What I can do is, I can simply, so let me draw the same neural model, where I have this addition and I have different inputs. Okay. One of the input I can put equal to 1 constantly, and the weight given to this corresponding input can be W naught. Okay. Whereas, to other inputs, I have the different components of the feature vectors, that is x1, x2 up to xn. Okay. The other functionalities remain the same. I have this non-linearity, and then I have get this output y. Is it okay? So, over here you find that output of this is summation of xi into wi, I varying from 1 to n plus w naught. Okay. And on top of that, I put this non-linearity, which gives me the output y. Okay. Again, I can have similar kind of decision that y will be set equal to 1 if this term is greater than threshold, it will be set to 0 if this term is less than or equal to threshold, and accordingly I can go for classification. Okay. So, find that in both the cases, the model that we have is closely similar to what we have followed in case of linear discriminant function, and we have seen that there are different approaches of designing the linear discriminant function. Okay. Like perceptron criteria, relaxation criteria, mean square error criteria, minimum square error criteria, and so on. So, what I have to do whenever I go for designing such a kind of neuron is that I have to select the weights or WI properly, okay, which was the purpose of having different types of criteria functions. We wanted to have different weight vectors, a weight vector which give you proper classification between two or more classes. Okay. So, here also the major task is to decide about these connection weights, okay, and that is what is done during training or learning of neural network. Okay. And as it is very close to what we have got in case of perceptron criteria, a neural network formed out of such neuron models, they are also called perceptrons. Okay. So, in the simplest case, I can have a single output single layer perceptron, okay, which is nothing but a single neuron like this. So, in case of a single output single layer perceptron, the neural network is simply this. So, now all this function we put in the form of a node, these two taken together can be represented by a node. So, when I say a node, the node includes both this adder which performs a weighted summation as well as this nonlinear unit. So, a node gives me this particular output for a given input. Okay. So, a single output single layer perceptron is a single node something like this. So, which has a number of inputs and one output. Okay. I can say that, so this is my neural node, or let me not use n because in many cases we are using n to represent the dimension. Okay. If I have a biased one of the inputs will be equal to 1 and the other inputs will be the different components of the feature vector up to say xm, let us say. Okay. And here my GIX, what this node compute is simply summation of WIXI, I varying from 0 to m. Okay. And we say that if this is greater than 0, then we say that the vector x belongs to class omega 1. Okay. If this is less than, or let us include equal also, if it is less than or equal to 0, we say that the sample x belongs to class omega 2. Okay. Now, in case of perceptron criteria, we have said that this weight updation rule was that initially we decide W0 to be arbitrary. Okay. When we had the perceptron criteria, initially we decided that W0, the weight, initial weight is chosen arbitrarily. Then at every iteration stage, the weight was chosen as Wk plus 1 was equal to Wk plus eta times y. Okay. This is what we had in case of perceptron criteria. Now, similarly, in this case also we have to have some weight updation rule which will update the weights of the input links. Okay. And this weight updation has to be done using the training samples that which are provided. Okay. So, we have to make use of all the training samples which are provided and keep on updating the weights until and unless we get the correct output. Okay. And since the training samples, we know what are the class levels of the training samples, then for a training sample I know what should be the corresponding output. Okay. So, if a training sample x belongs to class omega 1, I know that output should be equal to 1. If the training sample belongs to class omega 2, I know that output of the neuron has to be equal to 0. Okay. So, what I can do is I can find out what is the difference between the target output, if the actual output I call it as target output, that is what is expected, okay. And because of improper weights, improper connection weights, I may get an output which is not actually the target output, okay. So, the difference between the target output and the actual output is the error, right. And all the weight updation rules, connection which updates the connection weights in a neural network, tries to minimize that output error, because I know that what is the exact output, what should be my target output, and what output I actually get. So, I can compute what is the error, then try to minimize that error by modifying the connection weights, okay. So, over here you find that for a given input x, for a given training sample x, if I know that my output, the target output is say d, okay, whereas the actual output that I get is nothing but summation of wi xi, where I varies from 0 to m, okay. So, this is my target output, this is the actual output that I am getting. So, the error E is nothing but d minus d, okay. I can have sum of squared error from this. So, I can say that sum of squared error, let me write it as capital E, which is nothing but half of summation d, let me say that this is for a pth sample. So, dp, so I will have dp where p varies from 1 to capital N, where capital N is the total number of training samples. So, for every sample I will have an error, okay. Take the summation of that error, summation of square of the error, which gives you the sum of squared error, okay. Out of this you find that this sum of squared error is actually a function of w, where w is the connection weight, right. So, the simplest approach that can be taken is you try to minimize this by differentiating this with respect to w, okay. And as w has got m plus 1 number of components, okay. So, by differentiating this with respect to w and equating that to 0, I will get m plus 1 number of simultaneous linear equations, okay. You solve that set of simultaneous linear equations, which will give you the values of different components of w, okay. And you set that different values of w as your connection weights, and your neural network should give you the classification result whenever an unknown sample is fed to the input of the neural network, okay. However, as we have done in our earlier case, that instead of trying to solve this number of simultaneous equations, we can have sequential algorithms or iterative algorithm, which will iteratively update the weight vector or the connection weights, okay. And for that, what we have to do is we have to go for gradient descent procedure. Pardon? X is the input vector. Yeah. Xi is different for different pattern. Yeah. You mean to say that I should put it as like this? Does it really matter? Okay. If it is pth sample, yeah. If it is pth sample, I can put it like this also. So, this is the ith component of the pth sample. You can put it like this. Okay. So, we can again follow the gradient descent procedure. For that we have to take the derivative of this squared error with respect to our weight vector W. Okay. So, if I take the gradient of this, say del E upon say del Wi, which is the ith component of the weight vector, where this I varies from 0 to capital M, as there are m number of m plus 1 number of components, including that one that we have added as bias. Okay. So, this del E del Wi, if you compute this, it will simply become d minus d into xi. Okay. If you differentiate this with respect to Wi, then what I get is this d minus d, d is the actual output that I get. Okay. So, lowercase d is the target output. So, d minus d is the error that I can easily compute into xi. Okay. So, accordingly, our weight updation rule will be Wk is equal to Wk following that gradient descent procedure minus eta times d minus d into xi. Okay. So, you find the difference between what we had in case of perceptron criteria. In case of perceptron criteria, our weight updation rule was something like this, that Wk plus 1 is equal to Wk plus eta times y, where y is the vector. Okay. So, the entire weight vector was being modified simultaneously. Okay. And in this case, it is no, that differentiation you do, it will come this, because we are differentiating with respect to Wi, that is the ith component of W. So, jth component, that is Wjxj, which is independent of Wi, that will become 0. So, I will be left with only xi. Okay. The contribution of this xi into this error term was Wi into xi. Okay. So, what is this differentiation? Del E del Wi is nothing but, if I expand this whole term, because this is square, I will have 2 into this into del Wi of dp minus dp. Summation.
Is for pth sample and for pth sample
I am not, for the time being, I am not considering pth sample. Given a particular sample, what is the error? Okay. So, given a sample, the error is d minus d.
So, in that above equation, there is a
this is pth sample, this is for individual samples. This is for individual samples. I am trying to compute what is the error for an individual sample, and whenever I face an error, I am trying to modify the weight vector. So, you can say it is the pth sample where p is variable. Okay. So, this is what I have for an individual sample. Okay. So, a training sample which is fed to the neural network input, I know what is the target output, that is lowercase d. I know what is the output that I am actually getting, that is capital D. Difference between these two, my error. Okay. So, the weight updation rule in this case, unlike in case of perceptron criteria, where the weight updation rule was this, over here the weight updation rule is Wk plus 1 is equal to Wk minus eta times d, this will be the ith component, because I am talking about the ith component W only. Wik plus 1 is equal to Wik minus eta d minus d into xi, where xi is the ith component. Is that okay? So, this is what I have in case of a single output, single layer perceptron. Okay. Where this Wi actually represents the connection weight from the ith component xi. So, this is my wi. So, for every individual component I am doing it, right. And this single output neuron perceptron actually takes care of only two class problem. Okay. If the output becomes 1, I will say that the sample belongs to one class. If the output becomes 0, I will say the sample belongs to another class. Okay. But if I have multiple class problem, then this single output neuron model is not sufficient. I have to have a neural network having multiple number of outputs. Okay. So, I have one input layer where I feed in the feature vectors, okay, and I have an output layer where the neurons in the output layer are same as the number of classes that I have. Okay. The inputs are the feature components are fed to input layer, okay, which is simply passed to the output of the input layer neurons. Okay. So, these are my, say this is 1, then x1, x2, say this is xi, then I have this xm. Okay. I have the connections from outputs of each of the input layer neuron to the input of every neuron of the output layer. So, I have connections like this. Okay. So, it continues like this, and these are my outputs. Okay. So, I represent the connection weights as Wij. So, this Wij connection weight means that this is the weight of the connection from the ith node of the input layer to the jth node of the output layer. Okay. So, this Wij, this represents, say this may be my ith node of the input layer and this is the jth node in the output layer. So, this connection weight from the ith node of the input layer to the jth node of the output layer, this is represented by Wij. Okay. So, accordingly you find that if this output I say Yj, okay, so this Yj will be nothing but, this is Yj, summation of Wij xi, I varying from 1 to or 0 to capital M, okay, then the non-linearity which is applied at the output of the output layer nodes. Okay. So, for different values of I, the individual components are being weighted by the corresponding Wij. Okay. So, at the output layer what I get is Wij into xi. Okay. This also includes the bias because I have started for I equal to 0 to capital M. So, I equal to 0 means this W0j, this connection component will actually correspond to the bias or bias weight. Okay. So, I have this Yj which is a nonlinear function of sum of Wij into xi where I varies from 0 to capital M. Okay. In some cases, as we said earlier, that this nonlinearity can be a threshold function. In other cases, the nonlinearity can also be a sigmoidal function. Okay. Where the sigmoidal function is
Here, in input in node is only single, it may be multiple inputs like in
Pardon?
the first column of node.
Yeah.
Why there is single input is there? In previous case we have multiple inputs.
No. You are talking about this one. Here this is my, say actually each of these are actually nodes, because when I am feeding this input, where do I feed? Okay, these are actually nodes which are unity gain nodes. That means whatever is fed to the input, that is simply passed to the output. Okay, when I say the number of layers, this input layer is not really specified because this comes by default.
Single input is to input to this node.
Input to these nodes. Okay, here I said that this is single layer, single output neural network. When I say single layer, apart from this input layer, how many layers I have? So that is only one. Here also it is single layer. Here also it is single layer. I have only the output layer. Okay. Input layer comes by default. It is simply where do I hook in the inputs. Okay. So whatever input you are feeding here, the same input is simply passed to the output. Okay. And when these are connected to the inputs of the output layer nodes, every such input or output of the input layer node, that gets weighted by the corresponding connection weight, right. So accordingly, the input to each of the output layer nodes, that is input to the jth output layer node, is this. The sum of wij xi, I can consider that this is the input to the jth output layer node. Okay. Or this node I can break actually in two parts. Every output layer node I can break into two parts. One portion computes the summation and the other portion gives you the non-linearity, that is f. Okay. Coming to our initial nodes which we have defined. Okay. I have an adder unit followed by a non-linearity, right. So I can say that each of these nodes actually are broken into two parts. One part computes the summation, which is this, okay, followed by non-linearity f.
So here layer word, what it makes sense in weighted, that is layering or
no, that is not layering. Multiple layers I will come later on. Okay. So okay, because this question has come, let me just clarify this. See what we have done in case of this single layer, single output neural network. I get a linear equation of this form. This linear equation is equation of a single straight line. Is that okay? If the point when it is greater than 0 means a point which lies on the positive side of the straight line, which is given by this equation. If it is less than 0 means the point which belongs to the negative side of the straight line given by this equation. So this single layer, single output neural network actually divides the feature space into two half planes. One half is positive, the other half is negative. Okay. Extending that to this single layer multiple output neural network, you find that each of these output neurons actually defines equation of a straight line. Is it not? Because this wij into xi, I varying from 0 to m, for a particular value of j, it gives me equation of one straight line, right. For another value of j, it gives me equation of another straight line, right. So when I have, say, on this output layer, if I have a C class problem, I will have C number of output layer nodes, every node corresponding to one class, right. So when I have this C number of output layer nodes, each of the nodes define equation of a straight line, right, or each of them give you a linear equation. which is the discriminant function for individual classes. For classification, I will come later on. What I will do is, I will find out that for a given input, which of these output layer nodes gives you the maximum output, right? And the sample will be classified to that particular class which gives you the maximum output, which is nothing but the discriminant function that we have said in our earlier classes. Okay. And coming to our linear separability, because each of them are actually representing your linear equations. Okay. So, it is assumed that the classes are linearly separable. What you do if the classes are not linearly separable? Then this single layer will not be sufficient. I have to go for multiple layers. So, when I go for multiple layers, what I get is a nonlinear boundary is actually broken into linear pieces. So, piecewise linear approximation of nonlinear boundary. Okay. So, I will come to that later on. Let us stop here today.